All right. So our topic is London dispersion forces. This is in Unit 3. Here are hopefully some things that you might need or you want to use. Here's our objective. And what this objective means is, hey, I want you to know what these London dispersion things are, how they were made, basically, like how the molecules make them, and when various variables go up or down or change, how does that affect the LDFs? That's what it means. All right. Oh, now I all right, what I'm going to do now is just going to model how London dispersion forces are made and um, show you with the little picture. Let's say I had two molecules that should be about the same size, but this one's a little bigger, but it doesn't matter. And all molecules are the same, right? You've got your nucleuses and then surrounded by electron crowds. I guess you kind of are surrounded by electron crowds. But the electrons are constantly moving around, all right? And sometimes they even kind of, this line doesn't really exist because sometimes they may leave the molecule, or like it's a probability cloud. Okay, now let's just say stop it for a moment. This one's kind of evenly spaced out, but here I've got much more electrons on one side of the molecule. All right, that is known as, like, what that'll do is it creates a temporary dipole where this part up here will be negative. Okay, and the other side where there's not as much would be positive. Okay, but then it goes away and the electrons keep spinning. Okay, now this could happen where, oh, the electrons are on opposite sides. All right, so there, now I've got dipoles, negative negative, positive dipole. These are positive positive. Now they're called temporary because they go away. It's not permanent. The permanent ones are based upon more of an electronegativity difference. This is just about random electron movement. Okay, now let's say it ends up like this. Okay, we'll go like that, where they just align. This is going to create an intermolecular force because this end of the molecule is negative, this end's positive, and it's lining up with this. So I've got a positive and negative. So these temporary dipoles create some attraction between the molecules, and that creates is the intermolecular force. This force of attraction created by this random electron movement within the electron cloud. Now here's the definition. Okay, you can pause it. I want to, these, as it says here, these are in all molecules, right? And because all molecules have electrons, and the AP curriculum, you don't want to call them van der Waals forces. It's a Coulombic interaction, all right, meaning it's a positive and negative uh, electrostatic force. All right, now we're going to look at the variables that affect them. We've got two different molecules here. We've got I can't remember what the carbon word for 4 is, and methane and pentane. No, not, it's butane. Butane. Two molecules of butane and two molecules of methane. All right. Now, where is there going to be greater attraction? In general, the more electrons, the more possibility for electron this electrons to be randomly placed. So therefore, butane has the higher higher not van der Waals, London dispersion force, because there's just more room for it, rather than in methane. There's just less area for it to happen. There should be another hydrogen here. I didn't notice that till now. All right. So in general, London dispersion is the greater the size of the molecule, The more electron cloud you've got, therefore it's more polarizable. So butane is going to be much have stronger intermolecular forces. Okay, now this molecule is, I don't know the actual name of it, but you've got one carbon it's like isobutane. I don't know exactly what it is. One carbon bonded with four other carbons, so it's a 5 carbon organic molecule. All right, and you'll notice it's kind of has like it kind of has like a circular shape. So where would there be greater uh, London dispersion forces? This is playing upon surface area. Well, here there's lots of interaction. But when you make molecules circular, and I didn't draw the circles on that well, you that looks like more like a rectangle. You decrease, like in this case, the surface area gets decreased because if it's two circles interacting, they can only touch like tangentially. So therefore, the greater the surface area, the greater the London dispersion forces. All right. Now, this one, what's different about the ones on the bottom? The molecules on the bottom. Here we've got these triple bonds. We've got pi bonds. All right? And here we do not. You'll notice that the ones with the pi bonds have a nice, makes the molecule linear. When the molecule's linear, it's like really electron rich, or no. In the presence of these pi bonds, it's like electron rich, and plus it's linear. That also aids the molecules getting closer to each other. They can just like line up end to end. So in the presence of pi bonds, and the London dispersion forces will go up. It's funny, I never call them van der Waals forces, but in the video I do. All right. All right. Now, what would have a greater London dispersion forces here? Obviously, this one on the bottom, because it's got much bigger electron cloud and a much bigger, more polarizable. All right. Here are my sources. And I want to give you one last thing for your notes. So London dispersion forces depends on size of E cloud. All right. And as it increases, LDF increases. Okay? It also depends upon surface area. This is the same kind of thing. It's also directly proportional. All right? A third thing it depends upon are pi bonds. Pi bonds are when you have like the presence of a double or a triple bond. Okay? Then these go up, the LD forces also go up in general. All right? Now, the reason is with all of these, as these variables go up, the molecules become more polarizable. You're able to like make it have these temporary dipoles more effectively. And that's it.